Hello and welcome to my presentation on the Interplanetary Filesystem, or IPFS for short. IPFS is an open source peer-to-peer data storage and retrieval platform. Moving on, we have some related work. So IPFS is the culmination of many concepts, including but not limited to peer-to-peer overlay networks such as CAN, Cord, and Pastry, operational distributed hash table implementations such as the Kademlia implementation of BitTorrent, and content-based addressing as first proposed by information-centric networking and later taken up by named data networking, and also decentralized data management. So, this presentation is split up into two sections. The first will cover the four key concepts that I have on screen right now, and the second will cover the evaluation of IPFS. So, the four main pillars of IPFS is number one, content-based addressing, number two, decentralized object indexing, number three, self-certification, and number four, open participation. The first concept is decentralized object indexing. IPFS uses a distributed hash table that is based on Kademlia to locate data objects. So it uses the exclusive OR distance with its hash to ideally prioritize neighbors that are closer based on physical distance rather than physical distance not being a factor when traversing the distributed hash table. Each node will maintain 256 buckets of size 20 that partitions its known overlay network. As you will see later, the bucket size of 20 was chosen for a particular reason. New peers will join the distributed hash table as clients by default and are changed to servers if they are publicly reachable, so not behind NAT. The process works as follows. The new node joins and asks its known neighbors to initiate connections to it. If four or more are able to do so, then it is considered a server. The difference between a distributed hash table client and server being that a client only requests content from this network, while servers are also storing mapping records and providing them to any client that requests them. The distinction is done for performance, so that natted peers do not clog up the routing tables of their neighbors. The second concept is content-based addressing. Since content in IPFS is served by other peers in the network and not a central server, content is not stored according to its location, as multiple nodes that are storing the same piece of content, which in this context, they are called data providers, store the same piece of content for availability, as IPFS does not enforce nodes that store content to stay online. When a node requests a piece of content, it will perform two separate operations in parallel. The first operation is to query the underlying distributed hash table for the providers of the content by using the unique ID of the content in multi-round iterative lookups. In each successive round, the query will search for the nodes with IDs close to that of the content's ID based on exclusive OR distance. And each node that is queried will either respond with the requested content if they happen to be a data provider, or reply with its known neighbors with IDs close to that of the content. These new neighbors will be used for the subsequent round of lookup. The second operation is to request from all its known neighbors for the content using BitSwap, a sub-protocol within IPFS where the node will inform all its known peers of its want list, a list of all content a node is interested in. Then, these data providers will reply without coordination, meaning that data providers will not take measures to ensure data is not duplicated. This has the effect of increased network traffic, as in the general case, there will be multiple nodes replying to the same request. However, this has security benefits, as an attack on a distributed hash table will have limited effect, since a node will still be able to obtain content from their neighbors, as long as one is still able to respond. The third concept is self-certification. IPFS has the property of a self-certifying file system. What this means is that in practice, each piece of data is assigned a unique immutable address. This is called the content identifier, or CID. This is generated by taking a hash of the contents of the data. So if a node receives content it suspects has been tampered with, it can generate the hash on its own based on the content it receives, compare that with the CID to verify if the content has been tampered with, since the content ID is immutable. If the hash it generates is different from the CID, it knows that some foul play has occurred. The fourth concept is open participation. The process of joining the network as a node is quite simple. A peer will generate a public-private key pair, and currently IPFS uses RSA 2048. The ease of which an attacker can create an IPFS identity makes simple attacks a potential concern. However, due to the properties of the bit swap protocol discussed earlier, limiting the availability of stored data is quite difficult. However, users are still able to request data from the IPFS network even without formally joining as a node. This is done through gateways, which offer HTTP entry points into IPFS by using an Nginx web cache that attempts to track user demand. The second half of the paper describes evaluation data of IPFS. Data could not be collected directly due to a lack of centralization. However, since each distributed hash table server maintains routing information about their neighbor, active measurements using a crawler was able to gather data of peers by asking each peer about all the entries in their buckets. This was done until no new entries were found. Here, this chart describes the geographic distribution of peers. We can see that the United States and China together make up over half of all peers, with the US being 28.5% and China at 24.2%. After that, there is a sharp drop-off, with France in third place with 8.3%, Taiwan in fourth place with 7.2%, and South Korea in fifth place with 6.7%. Note that this chart includes multi-homing, that is, a peer that advertises an IP address that is associated with multiple countries. These two charts describe the reliability of peers. On the left, we can see that there are 1.4% of peers found to be reliable, meaning that they have 90% or above uptime. We can see that the United States and China has a large proportion of these peers, which makes sense if they have a lot of peers in general. However, interestingly, Germany has a greater proportion of reliable peers compared to how many peers it has in general. Now, on the right, we can see that roughly a third of peers are never accessible at all, and thus could be considered leeches, to use BitTorrent terminology. These figures are much more uneven, with China having a much larger proportion of unreachable peers. Now, what is the reason for this? One possible explanation is because of the Great Firewall, which could act as a NAT for all nodes located in China. This graph describes the churn experienced by IPFS nodes. Churn is a particularly important issue with any distributed hash table, as it informs the network how long a peer should retain information about other peers in its routing table to avoid dead nodes. Their analysis shows that 87.6% of session times are under 8 hours, and only 2.5% of sessions exceed 24 hours. So uptime on average is short, but varies depending on region. Still, the short uptime of peers is one of the reasons why the bucket size is 20, relatively large, and so the replication factor is high. These series of graphs describe the delay and retrieval performance of IPFS. For the delay, it is primarily composed of the time required to do the distributed hash table walk, which on average is 87.9% of the overall delay, while the RPC batch operation, which sends the record of data providers to selected peers, comprises most of the remaining delay. For the retrieval times, they are on average 4 times slower than an equivalent HTTPS operation. However, this can be partially explained by IPFS needing to resolve the address of the content as opposed to HTTPS. Still, this is much better than previous distributed hash table implementations. Here we can see the proportion of cache hits is roughly 46%, and thus any request that is served by the cache would have a retrieval delay of 0. If we have a cache miss, on the other hand, then we enter the IPFS ecosystem, for which 67% of the remaining queries are able to be served by the local IPFS node itself that the gateway is attached to, resulting in a delay of less than 24 milliseconds. Above that, requests will be served by walking through the distributed hash table, resulting in an increase in delay. Nonetheless, the use of caching in the gateway is able to reduce delay overall, regardless of the time of day. Some final notes. The authors find that IPFS has much better performance than, for example, the Kademlia implementation of BitTorrent, which tends to have numerous dead nodes that clogs up the routing table of peers. On the other hand, the largest difference compared to a baseline of HTTPS is the publication performance. However, the average end user is likely to be much more concerned with retrieval performance, which is much stronger in comparison to HTTPS. Lastly, IPFS does not currently feature any sort of incentive mechanism to encourage users to be more than leechers. However, the authors have not identified a problem with this, as participation is still widespread. Finally, here we have the references I used for this presentation. All the figures were taken from the paper, The Design and Evaluation of IPFS, a storage layer for the decentralized web. However, 2 other sources I used were the Performance Evaluation of IPFS in Private Networks and Mapping the Interplanetary Filesystem. Thank you for watching my presentation, and I hope you have a nice day.